We studied the process of emission, absorption, and scattering. Let's look at an example in nebulae. So this is the Trifid Nebulae. You see here different types of nebulae. You see this red one, which is an emission nebula. You see the blue one, which is a reflection nebula, basically dominated by scattering. And the absorption dark lanes here, or who have dust absorbing the light from behind. So emission nebula, they are red because they are emitting light in H alpha. You see here, these are the main lines that you would see in emission nebula. And there's this conspicuous red line, which is H alpha, which is red, and therefore they glow red. So these interstellar clouds, they can be referred to as absorption, which is the simplest one. They're just like a cloud of dust, gas and dust, absorbing light. You have a reflection nebula. You have stars here, and these are scattering the light from the blue stars that are in there. And emission nebulae, which are so hot that they start glowing in their own emission. So absorption nebulae, they are just a lot of gas and dust simply blocking light. As you see here, this is Barnard 68. You see the stars behind it, and then you see here this dark absorption patch, like a hole in the sky. Reflection nebula, they are basically the same as a dark nebula, except that they are illuminated by nearby stars. The dark absorption lanes have no stars to cast light, and therefore there's no scattering happening. But this here, in here, the dust is shining by reflected light. You have all of these stars around it, and therefore it appears blue. The light is reflected off and then sent our way by scattering. They're usually blue because they're illuminated by blue and white stars. And that same reason why the sky is blue. Blue is better scattered than red. In fact, yeah, absorption and reflection nebulae are the same object. Imagine a situation like this. You have the cloud, like there's this cloud here. You have background stars. You have red wavelengths, and you have bluer wavelengths. The red wavelengths are just going to go right past it. It's like infrared. So you're going to have less intensity. There's going to be absorbed, but it's going to pass. Most of the long wavelength light makes it through, but the blue wavelength here, the blue wavelength is going to be either absorbed or scattered. So what is going on is that the original light is deblued, right? That's the reddening. As you see here, this is a composition of 3 different filters showing that the red one, you see the stars in the red filter, but not in the bluer filters. And then you can have scattering when you have in the blue wavelength is coming here, and then it's reflecting off the surface. That's scattering. Then this is what you would see here on the left image. And you could also have reflection and absorption in the same nebula if you're looking from this line of sight, where you're seeing an absorption lane, but you're also getting some of the transmitted flux. Emission nebula, they glow by their own light. They're illuminated by nearby OMB stars. Very hot stars are emitting ionizing radiation. Now, when the electrons recombine after the ionization events, they emit light in all of the atoms' discrete set of wavelengths. For hydrogen, it just so happens that there is the 3 to 2 transition, this one here, that is in the optical. These other wavelengths are in the optical, so the Balmer series of hydrogen is in the optical. But this is the strongest one, H alpha from the 3 to 2. It happens to be a conspicuous red line, which is what you're seeing here. It's light from this transition. So emission nebula are an example of Kirchhoff's second law. They are hot gas, an ionized hot gas that is emitting an emission line spectrum, which is dominated by the hydrogen H alpha line. Now, emission nebulae are also called H2 regions. H2 is for ionized hydrogen, that's the nomenclature. Neutral hydrogen is H1, ionized hydrogen is H2, hydrogen that has lost 1 electron, it's single electron. And emission nebulae are red because of hydrogen emission in H alpha, but supernova remnants and planetary nebula, they're also emission nebula, but they're very colorful. This is a Crab nebula, which is a supernova remnant, and the Ring nebula, which is a planetary nebula. And that's because they are so colorful because they're chemically enriched. They're not just hydrogen. They have other elements in it. This is the spectrum of the Crab nebula. You see here, there is a prominent sulfur line, which is redder than H alpha, and have an oxygen green line. So you can combine these in 3 filters, blue filter, a green filter, and a red filter. And these are different combinations of filter and have these different colors because you're combining then these different emission lines. So the Trifid Nebula, so example, you have emission, these absorption dark lines, and reflection in the same nebula. And this nebula is in the larger Antares rho of Ophiuchi region. You have an extra example, which is this yellowish orangey, which is unusual reflection nebula from a giant red star. So I have here the reflection nebula, you have the dark absorption nebulae, you have an emission nebula in here in red, and this unusual yellow reflection nebula, which is actually created by Antares red star.